This is Sharon, and I am from CSC Regular, uh, and I am from CSC Regular, and now here I am. I'm going to I am going to show a presentation on a topic which is given to me. Basically, it is the name of the topic is analysis of series RL and RC, RL and parallel RL circuits when connected to an AC source. In this, we need to analyze the how they are connected and how they are connected and how basically they work and what is the equation of the current and what is the equation of the voltage and what is the phase difference and what is the uh, power and we need to discuss this all. So I'm going to discuss this all. Basically, basically, now I'm going to start series RL circuit. Basically, in this, uh, it contains a voltage, an AC voltage source, an AC voltage source, uh, and this we are going to uh, we are going to find the equation of the current and we are going to find the equation of the voltage and phase difference between them, how much phase difference between them and voltage across the resistance and voltage across the inductor as well. We are going to find it whether it lags behind current or not, whether it leads the current or not. We need to check all this. Basically, series RL circuit, the current, the same current flows through the resistance and inductor. So it is easy us to assume a current of equation something with phase I equals to I naught into sine omega t, where I naught is maximum current flown through the both the inductor and resistance and uh, we and we can by calculating their equation we can get to know the power, the phase difference between them, how much they are lagging, and all this we can find. So when we get to see the phasor diagram of the RL circuit, we'll be able to understand all these things clearly. So basically, in this, first we need to check the what the components are used in the series RL circuit. So I'm going to explain you all now. Now I'm going to explain you the components present in the series RL circuits. Basically, it contains resistors, and we know the property of the resistor, which resists the flow of the current, and an inductor, which opposes the sudden change in current, and an AC voltage source. Um, to particularly said, we particularly said a sinusoidal voltage source, and the equation of the maybe changes per time to time, and we can say v of t equals to v naught into sine of omega t, where v naught equals to maximum voltage supplied by the AC source, and omega is nothing but the frequency, the angular frequency we can say, and where t is time which is varying. So these are the basic components that are used in the series AC circuit. And now we are going to discuss the phasor diagram and uh, and the phase difference and the equations. All we are going to discuss. Now we get to see the circuit of the diagram. In the circuit, we can clearly see that voltage across the resistance and voltage across the inductor. In this, we can clearly see that a current I is passing through the both the resistance and voltage, and the net voltage to be taken as V. And when we get to the phasor diagram, you can clearly see that voltage across the resistance and the current is in the same phase, which we can observe clearly in the purely resistor circuit. And uh, and voltage across the inductance is leading by 90 degrees, uh, leading 90 degrees by an angle of 90 degrees, it which represents the purely inductive circuit. But when we try to add them sinusoidally, we get that V equals to under root over I square I r whole square plus IXL square, where XL equals to L into omega, where L is inductance and omega is angular frequency as said before. And when we rewrite the equation as I equals to V by under root over R square plus XL square, it simply represents V by Z. So the impedance of this RL series circuit is nothing but root over L square plus XL square, or root over L square plus L square omega square. So here we have discussed what is the impedance of the RL circuit. And next we are going to discuss the phase difference. Phase difference is generally represented by phi, and to calculate it, we shift the vector VL to that position, and from the figure we can clearly write tan phi equals to XL by R, and simply we can find the phase difference. And next, power is nothing but V into I into cos phi, where phi is phase difference. Now I'm going to discuss about parallel RL circuit. In this, basically we are going to analyze the how the current, voltage, and the phase difference between them is going to be generally when an AC source is connected across them. Basically, in this, we can clearly say that voltage is constant across the both RL, R, and resistance and inductor. So it would be easy to consider voltage as both both across separately, so that we can find easily our equations and analyze all the what you call phase difference and equations. So now I'm going to discuss the components that are used in the parallel RL circuit. Actually, it is nothing but the an AC source and a AC voltage source whose equations are also V equals to V naught into sine into omega t, where V naught is maximum voltage supplied by the AC source, and omega is angular frequency, t is any time. And as we get to this slide, the total power supplied by the AC source can be calculated considering the voltage and the total current. Basically, it is saying that power can be calculated by the total current and the voltage. P total equals to Vrms into Irms into cos phi. And we know that Vrms equals to Vmax by root 2. By that we can easily find. And phi is the phase angle difference between current and the resistor power. The resistor displays real power, that is nothing but I square R, Irms square R. And we move to the next slide. Here we can see the impedance of the parallel RL circuit when connected to an AC source. Basically, it is omega square, and it is in the form of real part and imaginary part. In this slide, we can see the clear clear real part and imaginary part. And when we get to the phasor diagram, it is clearly seen that uh, the the current that is passing through um, the current that is passing through the resistance is in phase with the voltage is in with the is in phase with the voltage that we connected in the parallel to the both resistance and inductor, and we can clearly see that the current is the current present in the inductor is lagging behind the voltage we connected across this resistance and inductor. So when we add them sinusoidally, we usually get these. So by observing these relations and equations, we can analyze this simply. So thank you for giving me this opportunity.